All right. So, did anyone else get the weather report that we're getting snow in Las Vegas? Yeah, so who wants to join me? So there's Mount Charleston, just north of here, ski slope. We're gonna go up there and we're gonna ski today. Who's with me? All right, good. So what would you do if you were prevented from going into work if there was a snowstorm? What would you do? Here at work, back home, what would you do? Oh, cheer. So you could join me and we'll hit the slopes. You know, we call it a snow day. What would your users do though? Cheer? What about the business? How would the business do if all of the users were unable to work for a day, or 2 days, or 3 days, or maybe even an entire week? The business could have a hard time with that. So, my name is Daryl Osborne. I'm a solutions architect. You know, it's great to be back in Las Vegas. Actually, I lived here a number of years ago, and my 2 oldest kids were actually born here. So it's great to be back here in Las Vegas. This week, it's very exciting because AWS, we're back here in town with re:Invent. Our partners are here, but most important, you're here, our customer. So we're glad that you took this week out of your schedule to be with us. And you know, we've already been here a couple of days. We've got 1 day left, so let's make the most of it. So let's go back to that question. What would your users do if they were unable to commute into work because of maybe a storm, or a natural disaster, or maybe a social or economic or some type of political event? What would they do? Well, if they were like some of the users that I would know, they would go ahead and get their laptops, open up their VPN client. They would pull out their token and try to connect. But if that was all of your users, what would happen to your VPN infrastructure? Your VPN headends would be overloaded. You would run out of connections. You would run out of licenses. The whole thing may just tip over. So I think we have 2 outcomes, maybe 3. So if it was snowing, you can go skiing with me and we could have some fun. But the other 2 outcomes would be just that they wouldn't be able to connect. The other outcome is maybe you thought this through and you over-provisioned your VPN infrastructure. You have the hardware, the software, the licenses already in place so that all of your users can connect remotely at the same time. What's wrong with that? It's pricey. How expensive would that be? 99.9% of the time, that hardware is going to be sitting there idle. Is that the best use of your company's resources? Well, we've got 2 great AWS solutions architects with us, Matt Lewis and Joe Fontes.
Hey guys.
And they're here to present some solutions to help us with this use case. So I'll turn the time over to Matt.
All right, thanks very much, Daryl. Okay, welcome guys. So we've really set the stage there. Snowstorm got you trapped at home. Is your VPN infrastructure really going to scale? So we're going to start with an overview on traditional remote access VPN solutions. So what do they actually look like? How do you connect to your corporate network via a VPN solution? Then we're going to go through the scenario, the what if, the disaster scenario, and then we'll roll through how to build a VPN solution on AWS, both in two different types of solutions. So I'm going to talk about the enterprise-based solution, so really using enterprise vendors and vendors you know and love today. And then Joe's going to come in and talk about the open source solution. And he's also going to expand on a few different features that on top of the enterprise solution. So we're going to roll through those, and hopefully you can get a bit of an idea on how you can build VPN solutions on AWS today. All right, so let's talk about the traditional architecture of a VPN solution. So at a very high level, you've probably got a corporate HQ with a lot of your users that are generally on net. So they're plugged into a LAN, they're within your security perimeter, they're within your network. You can control what they do, you can control where they can access through proxies, etc. You've probably got some other sites, and maybe a small site like a small office, for example. And they're probably all connected by something like an MPLS IP VPN. So a service provider network that you still control, it's still within your domain, almost. You've probably then got a data center with some data center stuff in it, some servers, and they're all connected in this nice ecosystem. Now, we've got users that want to connect to this ecosystem. So you need a secure, so an encrypted way of coming into that ecosystem and not opening it up to the rest of the world. So really these users probably have the internet, so they probably have internet connectivity, and they can connect through to your data center. The data center probably has internet connectivity as well. So from there, you'd probably deploy some VPN appliances that are internet connected, so they have public interfaces, or they're connected and can be reached via the public internet, and your users can then use an encrypted VPN to these devices. Once they connect to these devices, they get probably a static one-to-one NAT, so they've got an identifier and an IP within your network. You've extended your perimeter now out to the users, and they can now talk to your HQ, they can now talk to file servers, they can now talk to the private things that you have within your network. Now, keep in mind, in this solution, this is physical infrastructure. So as Daryl said, we've provisioned some VPN infrastructure inside our data center. So from here, if we look at the capacity of the infrastructure itself, it's probably going to be based on VPN users and bandwidth. That's generally what a physical VPN server is looking at. So how many users can you connect to that piece of equipment, and how much bandwidth can you put through that piece of equipment? Now, if we do have a snowstorm, for instance, and we all get locked in, all of your users start working from home. Your office is closed. Now you've got a large flash crowd of users that actually need to connect to your private network. So what does that look like? Well, as we start scaling out our users, our VPN infrastructure starts getting overrun. Our capacity gets overrun. So we breach the number of VPN users that we can support. We also breach the amount of bandwidth that our VPN hardware appliances can support. So we have a capacity shortfall here. And that means users can't connect. So what do? Well, you hit the help button. Now in our case, and I'll talk about what the help button actually is. It is a physical thing almost that you can press to deploy VPN infrastructure in AWS. So you've hit the red button, what happens now? Let's watch our enterprise VPN solution grow out. So first we need some requirements. What do we need this VPN solution to do? So we want one-click deployment. So how would we do that? Probably AWS CloudFormation template. So we build a CloudFormation template that deploys an AMI inside a VPC that's based on a VPN instance. And all of the other stuff that goes along with that. We also want to take advantage of our 5 advantages of AWS. So we've got agility, cost savings, breadth of functionality, the ability to deploy globally in minutes. So we have 11 regions worldwide. You can deploy in any one of these regions. And elasticity, that's the important thing here. So remember, we had a capacity overrun with our physical infrastructure. We want to try and get around that limitation. With that, we want complete infrastructure automation. So we don't want to have to actually go and rack and stack something. We don't want to have to touch fingers to keyboard and deploy something. We want to click one button and have it all automated and deployed for us. And lastly, fault tolerance. So how do we build the solution in AWS? Well, we've still got our private network. We haven't changed anything there. We've still got our data center. We've still probably got some other servers in the data center. So you don't need to move those to AWS. You can still connect to those. We're not talking about a lift and shift or anything like that. We're only talking about connectivity. So we've still got our users. They've still got the internet. But now, instead of coming directly to the data center, they're actually going to an AWS region. So within the AWS region, we're deploying some instances. So in this case, some EC2 instances within a VPC. Now, we can connect back to our data center either via a direct connect if you have one in place, or you can just use VPN, and you can automatically provision VPN as well. Now, AWS by default is connected to the internet through an IGW if you so configure that. And now our VPN users are actually VPNing to the AWS infrastructure instead of VPNing to the data center. So now, as we turn on more users or more users are working from home, our infrastructure is going to automatically scale. Okay? So instead of the capacity shortfall being a distinct line that we can only overcome by deploying physical infrastructure, it's now something that grows with our infrastructure and also contracts. So when you don't have a large number of VPN users, you can contract your infrastructure. Now, these are all 101 tenets of AWS where there are advantages that you can take advantage of today. Alrighty. So depending on whether you're coming in through a direct connector or a VPN, the architecture is a little bit different, but I'll talk about that. Okay, so let's look at the architecture in AWS. Let's really zoom in here. So we've still got our users. Nothing's changed there. We still have a data center, some other servers that are sitting in that data center. Now we have our Amazon region. So you select a region to deploy the VPN infrastructure. From there, we deploy a VPC. Now, what a VPC really is, it's a private isolated section of the AWS cloud that you deploy instances in, or EC2. That's where your EC2 instances are going to sit. Okay, so you have your Amazon VPC. You designate a CEDAR address range for that VPC as well. Then we've got some availability zones. So these are our fault domains within an Amazon region. So consider instances that are deployed in multiple availability zones to be not in the same fault domain, so that if one does go down, one AZ does go down, your other instances won't be affected. So in this case, we're choosing 2 availability zones. You can choose more than one. There's generally 2 to 3 in most regions. From here, we deploy our subnets. So I'm actually deploying a few different types of instances. I'm deploying a VPN instance in this case, and I'm deploying a worker node subnet. So I'm deploying a watcher or a witness or a worker node, which is going to be doing a bit of processing for me. And I'll talk about how that works in just a moment. But ultimately, I'd like to have that as a service, and I'll talk about that too. Okay, now we've got our VPN instance subnet. From there, we've got an IGW. Now, don't be deceived here that I've actually got 2 IGWs. We only have one. So with a VPC, you can attach an IGW and a VGW. The only reason why I have 2 up here is just to show the flow of traffic. If I had one, the traffic would go in and kind of come out again. And that's really what's happening. But just for ease of demonstration here, I've got 2 IGWs. Okay, then we have Amazon Route 53. So this is important to load balance across the VPN instances. So what's basically going to happen is a user will try and hit a CNAME to VPN. I think you had unicornrentals.com or something as our company. So vpn.unicornrentals.com, and that will be resolved to a VPN instance. So we can use Route 53 to load balance across the VPN instances we deploy. So we're using Route 53 for DNS load balancing. Now, DNS load balancing is probably not the best when you've got a web server or a lot of constant traffic like this, but for this case, it's actually perfect because the VPN user resolves the CNAME to an IP address, and we can just return a different IP of a different VPN instance as we go along, and it actually works quite well. Okay, so we've got our worker nodes deployed within our worker node subnets, and I'll talk about those and what they do in a second. Then we've got our VPN instances deployed in our VPN instance subnet. Now, you'll notice I've actually got some downstream VPNs. Now, we do need to build some downstream VPNs in this case, whether we're connecting to another VPC, or our data center could be another VPC, or if we're connecting to your on-premise. The reason being, we don't actually allow transitive traffic through a VPC today. It's not something that's allowed within the Amazon infrastructure. So what we're basically doing here is building a VPN to a VPN instance and then using the the downstream VPN tunnel to either our on-premise data center routers or another VPC. In this case, in the diagram, we're using our on-premise data center routers. Now, we're actually using on the downstream VPN, in the actual solution itself, we're using IPsec, and we're also using BGP for load balancing. So our VPN instances had BGP capability. So if one goes down, the routers within the data center can actually load balance across those if need be. All right, so we're putting our VPN instances in an auto-scaling group. So that's quite important. We want them to scale out and scale in. So in this case, I've got a minimum instances set to 2. So at a minimum, we've got 2 VPN instances that are taking traffic, and these can scale as we need to. So we can deploy multiple VPN instances with the auto-scaling group and provision the downstream VPNs as well. Alrighty, so for the load balancing, DNS load balancing, basically a user will come in and hit Route 53, who's the authoritative DNS for our vpn.unicornrentals.com. The response will be one of the VPN instances. And then the VPN user will connect to the VPN instance using the VPN client. So you can use various different clients. In this case, we're using an enterprise solution with an enterprise-based client. So as our users connect, they get connected to different VPN instances. So we're basically load balancing and spreading the load across the instances themselves. Now, one important point that we needed in this solution was two-way communications. So our users themselves actually had soft IP phones, which they run on their desktop, and they needed inbound calling. So we needed a way to identify each user over the VPN session uniquely. So what we were actually doing is matching the instance IDs, and actually we were matching the IP address of the worker node to a /20 subnet. Now you'll notice our CEDAR address range is actually a 10.0.0.0/16. We've also got a 100.64.0.0/20, for example, allocated to each VPN instance. So what happens is the VPN instance, when a user connects to it, will take an IP address out of this /20 range, which is outside of the VPC range, and allocate that /32, in that case, to that user. So as, let's say someone picks up the phone in the head office and wants to call someone who's VPNing in, there's a unique IP address that you can have two-way communications with. So we're doing a static one-to-one NAT to each one of these /32s on the VPN instances themselves. And we were actually tracking that database, or we were just using a text file in this case, and I think Joe does some pretty awesome stuff on his using one of our database solutions. Okay, so auto-scaling integration, what does it actually look like? So when you think about the worker node, what's it actually doing to integrate these VPN instances into auto-scaling? So we have our worker node and we have a VPN instance. We're actually polling the VPN instance. The VPN instance in this case, when it was an enterprise-based solution, we're polling the VPN instance using SNMP polling. We're taking those SNMP stats and then pushing them to Amazon CloudWatch. Okay, so you can have custom metrics in Amazon CloudWatch. CloudWatch then has the ability to trigger alarms as we reach our capacity shortfalls. So we know what the limits are and we set them in CloudWatch, and we trigger an alarm which triggers an auto-scaling event, and auto-scaling then spins up multiple instances based upon our policy. Now what happens then is our auto-scaling group is referencing an AMI. The AMI is something from the marketplace or something we've built, which is pre-configured, but there needs to be some static or dynamic configuration. So far this is only static configuration on the VPN. So as the VPN instance comes up, we need to dynamically configure it somehow. So as we're launching more instances, we need something to get notified that we have more instances and then push a configuration to these. Okay, so for the configuration of the VPN instances, we've had an auto-scaling event. The auto-scaling group has launched some instances. So in this case, we've launched another VPN instance. Using an instance launching hook or a lifecycle hook, we push a notification to SQS, or Amazon Simple Queue Service. What we then have is the worker node polling the simple queue service on every 30 seconds or something like that, looking for new instances. So as a new instance comes up, the ID of the new instance and the IP address gets pushed to the simple queue service via the launch hook notification. Once the worker node has the new instance ID, it then builds a config that it needs to. So once it builds the config, it'll actually push that out to the VPN instance itself using the API on the instance. After the instance has been configured and is ready to go with its dynamic configuration, one of the pieces of the dynamic configuration was that /20 address range we needed to allocate to each instance. We then put the worker node in, we then put the VPN instance to work. So we notify Route 53 that we have a new instance that's ready to now take VPN users. So we've effectively scaled out our infrastructure automatically. Okay, so on the worker node, I've just got a sample configuration. Now, in this case, I'm building a VPN tunnel back to another VGW. So in this sample, I've got a VPC where the on-premise data center was actually another VPC with a VGW attached. So you can see here we start with we've got a call to grab the public IP or with the instance ID, so we're getting details of the instance itself. Then we're going to create a new CGW in this case. So the worker node's got the AWS CLI, and it can go through and create a new CGW, which will actually be the VPN instance, because in this case, the CGW is the VPN instance, and we're connecting via an Amazon VPN connection to a VGW. We're also creating a VPN connection, and then the last thing that you see here is just doing a HTTP post, which is taking the config that we've actually built in the background here onto the enterprise appliance itself. Now, if we have a look at that config, and we were actually using a Fortinet FortiGate for our enterprise solution. So this is actually a real Fortinet FortiGate configuration. And you'll see that we have various different variables inside the configuration itself. So the worker node knows to poll AWS and gather the information that we need, and then replace each of these items with the various pieces of information it needs to build out the configuration on the VPN instance. So overall, I think the configuration for the FortiGate was about 3,000 lines. And we had probably about 20 different variables that we just needed to populate in that. Alrighty, so overall, we've basically got a solution where the VPN instances can scale out automatically based upon the users and the bandwidth. So we're polling the VPN instances for their bandwidth and the users' utilization, and then triggering an auto-scaling event from there. Once auto-scaling is triggered, we push something to SQS via a lifecycle hook or an auto-scaling hook, and then our worker node is actually polling that SQS and building a config, and then building the infrastructure needed to support the VPN instances. Now, one last point I want to make here. Well, users can grow with no infrastructure shortfalls or capacity. But one last thing I wanted to make here, a point I wanted to make, we had worker nodes inside our VPC. This is actually their physical infrastructure, or they're actually EC2 instances that is something you can touch and you can configure, right? We wanted to replace those with something like a codified as a service. Now, we actually have Lambda, AWS Lambda, which can run code as a service. We wanted to replace the worker nodes with Lambda in this case, so we could completely get rid of the worker nodes altogether. Unfortunately, at this point in time, Lambda only functions outside of a VPC. So with cron on Lambda and the ability to function within a VPC, this architecture would actually get a lot simpler. So we would just have a service that's running code, polling SQS, doing auto-scaling, and everything would be just there and running without having to manage these EC2 instances as worker nodes. But in this case, the worker nodes actually work quite well, and that's quite a common solution we see on AWS. Cron, I think, was? Possibly. I think what we actually need Lambda to do is run inside the VPC, not just access the VPC. So you can access the VPC, and that would be fine. But in our case, we actually wanted Lambda calls inside the VPC so we can have that security perimeter still around the whole VPC itself. So I think that's something we're still looking for. But pretty awesome anyway. Okay, so from there, I mean, I was using the Fortinet FortiGates as an enterprise-based solution. They were actually quite good. I mean, the support guys, I've got two of the FortiGate guys or Fortinet guys here in the front of the room. They were fantastic in configuring and deploying this solution, and the support was excellent. But what if you wanted to kind of roll your own and just kind of roll with things like that? Joe?
Yeah,
do you
absolutely.
want to talk about that now?
Thank you.
Awesome. Thanks.
So what if your budget constraints don't allow the use of other products, or if you simply want to put together a proof of concept? How can we go about doing this with some of the open source tools that we have at our disposal? Throughout this segment, we're going to be covering some key areas. We'll start off with the design overview, go through a little bit of how we're going to be load balancing, the setup of a dedicated routing instance, the VPN config, some details about CloudWatch. But I wanted to, as Matt mentioned initially, this is going to be a slightly different configuration. To make it a little bit more exciting, I didn't want to just rehash the same configuration using a different tool. So we're going to be doing things a little bit differently. But as a recap, Here's the infrastructure that Matt first presented. We've got our auto-scaling infrastructure that scales up in order to meet demand. Just like you mentioned, there's a multitude of options in order to connect this VPC infrastructure back to your corporate environment. And so we'll be looking at a few of those different options as well. In our example that we're going to be using here, we're looking at a global workforce, right? So if you have an organization that's maybe based out of New York, but has staff that are based all around the world, then you want a VPN solution that meets the needs of the entire staff. So, here we have the map that lays out our regions, along with the number of availability zones in each region. And we're going to use those as the endpoints for clients to be able to connect. Here's an overview of the final product that does scale with the needs of the end users. This is the design overview for a single AZ implementation. The end goal of today's discussion is going to be multi-AZ, multi-VPC, and multi-region. In order to be able to scale, in order to be able to isolate where those resource constraints are, and also for high availability.
So Joe, I think I only really talked about a single VPC deployment. So you're deploying multiple VPCs then in every region?
Standard is one VPC per region,
Okay.
But depending on your business needs, this certainly can be duplicated into multiple VPCs per region.
Okay, awesome.
And here's the overview of what it's going to look like once we have those multiple VPCs, once we have those multi-regions. It's just like Matt mentioned with CloudFormation, you can use a CloudFormation stack to roll out these initial implementations, and then utilize services like AWS auto-scaling in order to scale the solutions that have been rolled out. Kind of step one is we're going to reserve some IP address ranges. As part of the proof of concept, we're going to be working with static routing today, but at the end I'll talk about some of the different options we could have had with OSPF and BGP. But right now, one of the first cases we want to avoid is subnet overlap, right? I really hate having to do source netting when you get your client IP address overlaps with your corporate IP address, and it makes things difficult. Even if you're running SIP traffic and you have S-ton, for instance, it's still preferable to be able to do those direct IP connections. So we're going to be using some of the terms from this example. The VPN address pool, that is a reserved /16 broken into multiple /24s. We're going to be isolating traffic between a private subnet, a public subnet, and a routing subnet. So we want those addresses reserved as well. The X denotes which region it's going to be running in. So for instance, we'll assume the corporate network is 10.100. We'll assume Northern Virginia is 10.101. Maybe Oregon is 10.102. And so the IP schema would look like, for the private subnet, for example, in 10.101 Northern Virginia, we have multiple private subnets across different availability zones because we should have multi-AZ deployments. And so those three would be 10.101.1.2.3. And this allows us to span across multiple AZs. That same idea works for the public subnets as well as for the routing subnets. And once again, just to make sure that we can simplify those routing destinations and also make sure that we know where the traffic is destined to, and we're not going to reuse these IPs in the public.
So I need unique IPs in every VPC worldwide.
Yes, so you do a, for your private subnet, for example, it'd be a unique /16 per VPC within each region. With the VPN pool, you would be assigned multiple /24s, one per VPN server that you're firing up.
Okay, and I'm asking these questions because Joe did a little bit more advanced work than me, so I want to try and steal some of his ideas and implement it in my solution as well.
Here are the IP reservations as used in one example. You can use dynamic assignment of IPs within each subnet. I find it easier to just statically assign things for like the routing instances. So all of my routing instances are 10.101.2.11.4.11.7.11, so that when I ping across ping across multiple regions, I don't have to look up, what the IP addresses are or what the, public DNS and private DNS entries should be. So yep, here we have the exact examples. In the middle, you'll see the routing instance. It's between those three subnets to denote that it has an ENI, an elastic network interface, in each subnet. Same thing for the VPN instances. They span two subnets, which would be the private and the public subnets, and that is to denote that they have one interface in each subnet. So how do we decide what subnet gets assigned to which VPN server? As Matt mentioned, there's a lot of different ways that you can do this. They were using flat files in the previous example. In this example, we're going to be using DynamoDB, and this is a screenshot of an actual implementation that we're running. So the entries that you see here are unique network ID and what subnet is assigned per VPN server. Now, if you have one subnet assigned to two unique servers, that's going to cause some issues because it's not going to be as clear cut what direction we should route in order to get back to the client traffic, right? So in this example, you get an instance ID as well as what region that instance exists in assigned to that subnet. Just so everybody's aware, you can have the same instance ID in multiple regions without that instance being associated in any way. So this is why, to get the true uniqueness, it is instance ID and region.
So I think one of the issues that we had with the worker nodes, we had flat files on those.
Yep.
And if we had a worker node that went down, we would have to replicate that flat file somehow to the secondary worker node. So we'd have to keep track of that. It was a static thing. So I think maybe if I use DynamoDB instead as an IP allocation table, that would be a pretty awesome solution.
And the beauty is that it's already designed for high availability. You don't have to be a DBA. This isn't something that, you need to be able to maintain. This is a regional construct, so it will fail over automatically, which, is something that you just don't want to have to build. I mean, we could have used alternate open source database engines, but that just increases our administrative overhead.
So if you think about it, I was building an IP allocation system with a text file. I could have built a queuing server with an EC2 instance, but instead I used simple queue server. So it's probably a good idea to see what other services I could use in place of things where I'm doing manual work. In this case, DynamoDB for IP allocation.
Yeah, and just as easily, we could have gone with RDS with the multi-AZ deployment.
Okay, that would have been cool too.
Yeah. So I mean, there's a lot of options on which way to move forward, and it's not just with the AWS services, and there are multiple ways that you can link the AWS services together. Using Kinesis as opposed to SQS type of thing, or we could use RDS as opposed to Dynamo. But just as we can have different options there within the routing instance, we have different options too. We're using OpenVPN for the point-to-point connections. It could just as easily have been OpenSwan. So, Matt got into using DNS Route 53 for the load balancing of the VPN instances. We're going to use the same method here using Route 53. We're going to do it at two different tiers. First is going to be a geo resolution, and the second is going to be a latency-based resolution. So let's say you've got your staff sitting in Frankfurt right now, and they are buried under 10 feet of snow. You only want to have to scale the location where that traffic is destined to. So you have somebody, so here's a great example, the UK, right? It's a little bit better. So the UK sits between, the Ireland region and the EU Central region. So with something like geo-based routing, you can say, well, everybody in England should end up in the Irish data center. So they'll resolve something like EU west1.vpn.unicorn.rentals. And then once they have that name resolved, it'll then further go down into which is the lowest latency connection that they connect to. So if you have 10 instances of the VPN running in EU West 1, they'll be connected to the one that is the lowest latency.
So does the UK get snow? Oh, no, I've never been.
I actually don't know. I can tell you Seattle doesn't seem to.
Yeah, occasionally, right?
Right. And this is what it kind of looks like for the breakdown of that latency-based routing. So when you get to the second tier, you've already been assigned a region that you're going to be connecting into. This just decides what particular instance you're going to be utilizing for that VPN connectivity. And here we have the overall workflow that you'll be using. So, VPN dot region name dot domain name, and then go down to the latency figure. And there's a lot of options with this. This is just one example of how we can do it. We could use different weights for maybe machines that can handle more traffic as opposed to machines that have less bandwidth. We can use latency-based routing without geo, or just standard round robin type of load balancing. So, I mean, a lot of it is up to personal preference, and we'll be talking about a little bit of those preferences in a bit. But in scripting out this actual process, here's an example that we're using. And this is an example that we have running in one of the VPN instances within the proof of concept. So here we see we're adding a Route 53 resource record, as well as we're creating a health check. So, I don't want to go too deep on it, but with the health check, usually when you create a health check, you're looking at, is that TCP port listening? And that's the extent of your health check. But what we wanted to do is really make sure that this service is running and is running correctly. So, our health check actually has a call, an HTTP call to a status page of the actual instance that's running. And that double checks things like, are the routes set up properly? Are the subnets attached properly? Are the DNS entries in there properly? And as long as it passes, it'll pass the health check, and then it'll be a part of those that latency-based resolution. And if it doesn't, then it won't be added to the cluster, and it won't mess up all these VPN connections. If you have 10 VPN servers in one region, and you have 1/10 of your customers or your employees reporting an error, that can be kind of tough to track down. So really, we want to get them those machines out of the rotation with something as simple as an automated health check. So one of the differences with this configuration is the use of a routing instance. There's multiple ways that we can connect the routing instance back to corporate. There's multiple ways that we can connect the routing instance to another routing instance to get that cross-region VPC peering. There's a lot of different things that we could put on that routing instance to make it a little bit more useful and a little bit more flexible.
So Joe, I like the idea of the routing instance. I mean, it seems logical that you have a device that you can send traffic through and put some policy in place, but what are you actually using? Like a Cisco CSR? Is it like a Viata or a Vios?
Great question, right? I mean, it's kind of like, what's your personal preference?
Okay.
I'm pretty sure everybody is familiar with this third-party ecosystem that we have, and how many vendor-supplied products we could put in place. In the proof of concept, since we're sticking with open source, we're just going to use a standard Linux box, and that's more than capable to route the traffic.
You can do that with a standard Linux box?
Oh, absolutely.
Amazon AMI?
Yeah, absolutely. Even especially with the Amazon Linux AMI, where it has the network pass-through, the SRIOV, built in and turned on by default. You get this box that's capable of routing with just a few simple changes like IP forwarding.
So SRIOV, guys, hands up who uses instances with SRIOV or knows what enhanced networking is. Couple of guys. I think that's a big thing with our customers, that we do get questions about how much throughput an instance can actually get, and in a lot of cases, if a customer's having issues, they're not using one of our enhanced networking instances. So in your case, using SRIOV, we're pushing some of the TCP stack onto our hardware or into the PCI controller, which is giving you more throughput as well. Which is
absolutely.
pretty awesome.
I mean, and you want to be able to take advantage of that. If you look through the instance type, some will have, they'll have different levels of networking capabilities, especially if you have a 10 gig instance that you're running. You want to make sure that you've enabled all of the features in order to take full advantage of that network capacity.
That sounds like a pretty beefy routing instance.
Yes, yes.
Okay, cool,
Yeah.
cool.
So within our example, we did not go with a 10 gig, but it's still quite quick. And so here's a example configuration that we use for that point-to-point connectivity between two routing instances. Like I said, there's a bunch of different ways to do this. We could have used OpenSwan with a connection to BGW. We could have done OpenSwan to OpenSwan. We could have, in this example, we're using OpenVPN to OpenVPN. If the two VPCs are in the same region, we could use cross VPC peering. So there's a lot of different ways that we can do this, and it's kind of like what fits your personal preference here. This is an example of the commands that we run in order to set up that point-to-point, and this is also something that's that can be automated with the CloudFormation template when that's deployed. But when we look at the path of the traffic that comes through these routing instances, what we see is an opportunity, right? Just like I believe that I mentioned, you can deploy a VPN as a split tunnel, but in anecdotal experience, more often I've had requests to just funnel all traffic from the VPN clients through corporate, and usually that's to enable something like web filtering. And web filtering has some overhead. Maybe it's something simple like a caching server, so you want to deploy Squid as a proxy, as a invisible proxy in the middle. Maybe you want to use network access controls, right? Open source, we could use packet fence. Maybe you just want to get an idea of what does my corporate traffic look like running something like NTOP to be able to graph out, how much of this is HTTP, how much of this is like MQTT, and then, basically just get an idea for what hazards are on the network as well. So if you deploy maybe Snort on one of these boxes, this could be a source for IDS traffic. When you have all of the client traffic, streaming through these route instances, there's a real opportunity there to be able to find things, maybe issues that you ordinarily wouldn't be able to find if you did a split tunnel route. If the Trojan traffic, or even something as simple as have they installed a toolbar, you can discover that with IDS sensors.
Configuration on the right-hand side says 10.100/16, and the little box down there says 10.100/7/24.
Oh, yes. So what we're looking at is when we have these point-to-point routes, we know that an entire /16 exists in this one VPC. So we're saying, even if we're not using it, just send all of that, all of that /16 over. But we're only using some chunks of it. So, but I mean, you still have the capabilities to deploy additionally. So with a static routing environment, which we're using for this proof of concept, to make it a little bit easier to just visualize, we just say push, all 10.101 traffic through that one routing instance, so that, once it gets to that routing instance, it'll figure out what subnet to pass it to. But we just know that everything that's 101 should definitely go to that VPC. So it just makes it easier for a static routing scenario. We'll go through some of the different examples that we could use if it was like OSPF or BGP, but we're just looking at this as like one example. Like I said, there's so many different ways that you can put this together. And, and here's an example of the routing table that we're going to be utilizing. In this example, we have some configuration samples that you enter manually, like the default route. If you notice the 10.33 entry here, that was automatically created when a VPN instance came up as part of the boot process. It grabs a/24 that it can use, and then it just enters it into the routing table, pointing it to the ENI of the instance. So we've talked about some of the things that we could use with the VPN server, with the routing instance, but now to look at the individual VPN servers. The routing instance, we can take advantage of so many opportunities, like I said, and since it's geographically closest to the end users, there's a lot of additional stuff you could do. Like, let's say that you want to put a DFS replication server over there. Have the documents that these employees are editing, have them be as close to the end as possible, and then maybe they're editing these documents within the region, and it's replicated back via DFS over to back to the corporate network. You could put read-only domain controllers over there. You could put application servers over there, just have them replicate content back. So there's really a lot of opportunity to kind of save bandwidth in between each point. So with the actual VPN deployment, here are some of the steps that we follow in order to get an image ready for this scalable VPN solution. So it's your usual stuff with application servers. You want to get that baseline image created. So this is the same whether you're putting together an Apache web server with maybe a custom application, or in our case, if we're putting together a VPN server. So we want to get that initial image created with the startup scripts that allow it to be automatically added into this VPN configuration. We're going to go over some of the scripts in a bit, and once you have this image, we're going to create a launch configuration, which is what auto-scaling uses in order to add and remove, in order to add new instances into that auto-scaling group. So, you don't have to read all of this. These are kind of some high-level steps that the individual scripts are using. The VPN config script, that's where you get a lot of variable information. So, is everybody familiar with getting EC2 data elements from the meta call? Yeah, all right, so yeah, everybody's pretty familiar with that. So yeah, the VPN script is what we use to get, the instance ID, subnet ID, VPC ID, all that basic stuff that we need in order to create routing information.
So this is almost what I had the worker node doing in my solution, right?
Yeah.
Except you've got it on the VPN instance now itself.
Right. So yeah, we wanted to, it's specifically on the VPN instance. The VPN instance is the one that does the call to Dynamo in order to get what is my subnet assignment, and then to update Dynamo and say, this instance has this subnet assignment, so nobody else can have it. And that actually comes up in the assign address script. So that's when you get your subnet assignment, and then you go to the next script, which is checking the routes. Is there already a route to this subnet that exists? If so, we're going to delete it to create the new one. If not, we're just going to create the new one, and it's going to be that route entry that we pointed out, which is this /24 pointing to the network interface of the VPN server. We just like we talked about with Route 53, there's our DNS script that says, is there already a DNS entry for this? If so, it's probably old, let's delete it. If not, let's just add it to there so that it's part of that latency-based routing. And then finally, the CloudWatch metrics that we're collecting. We're going to go through that in a couple of slides, talk about the different options that we have when it comes to scaling and what metrics to use when it comes to scaling, because there's a lot of different things that you can do with that. So with some of the tools that we were talking about earlier, using Snort, using web filtering, using web proxy caching, network access controls, using NAC. Here's what that traffic flow looks like. You have the end users coming in through a public interface. They're hitting the VPN instance, and then they're routing through to the route instance and back out via the route instance. And so this is the way that the route instance is able to capture all this traffic heading out. If it's destined for the corporate network, it's not going to go out the routing instance public interface. It's going to go across the routing instance routing subnet. There was a command that needed to be run that does force that traffic in this pattern. We add a new routing table to the instance such that all VPN traffic, which is part of that 10.33.4, I think, for this example, When it goes to hit a default destination, a default gateway, automatically it would assume, oh, I'll just go out the interface that I just came in, which is, probably Ethernet 0 of the VPN instance. But we don't want it to go in that direction. So we create this alternate routing table to say, if traffic matches this CIDR, we're going to send it over to the routing instance, and then that routing instance sends it out to the rest of the world. Just as I mentioned, we're going to be talking a little bit about the CloudWatch options. So this example is the script that allows us to scale based upon number of users connected. This creates a custom metric within CloudWatch, and it's per instance. One of the things you want to pay attention to is the use of dimensions here. Within CloudWatch, if you set a dimension, and my example is the most used example within the documentation, which is to use instance ID, but you can set your dimensions as maybe a department, you can set your dimensions as whatever you want, but this allows you to break down those stats. So I can say, just report on this one instance ID, how many users has it seen across the last month, and let's look at what the graph of that looks like. But this is the example that we would use to scale based upon number of users connecting. Let's say that you have these 2 users connecting, but they are very bandwidth intensive users and they need to get every piece of bandwidth that they can. You could instead scale on the built-in metrics of network bytes in and network bytes out. So it would scale to meet bandwidth demand rather than individual demand. So this is a business decision, a leadership decision. Do we want to force people into 100 people onto one instance where they have to share the bandwidth, or should it scale based upon that bandwidth need? So here's a look at what those custom CloudWatch metrics look like. We have the graphing that shows here are the number of users that have connected in this amount of time, we can do reporting based upon instance ID. It's a very flexible platform, and you can pass in custom metrics of your choice. So we have our metrics that are coming into CloudWatch. How do we do something based upon those metrics, right? So we're going to create an alarm, a CloudWatch alarm, and we set the variables for this. So for example, let's say that we stick with the user count, and we say that on the type of instance that we're running for this VPN instance, we know that we can get 100 VPN users onto this instance with the amount of bandwidth that they should have. So when should the alarm kick off? At 100? Because that gives you no time to actually scale the infrastructure. So you have to make that decision here depending on, and you figure how fast do people scale up, how fast do we need to scale up. So maybe your threshold is 60. So once a VPN server gets once the average of all VPN servers hits 60, it starts to scale up so that you don't hit that threshold and have users really lagging along. But once again, this is a business decision, something that you'd have to work out, and it impacts some of the financials as well. So auto scaling, this is kind of the big important piece of all this. Just as Matt mentioned with all those graphs, we want to be able to scale up to meet demand, and we want to reduce our footprint when demand is lowest. With an implementation like this, like if England is covered in 10 feet of snow, but everything's sunny and rosy in the rest of in all of the United States, we're only going to be scaling up the data center that England connects to. So what you need your baseline configuration, which is maybe we always want 2 VPN servers running in each region, and you always have that routing instance running in each region. So one of the things I really want to point out is the opportunity to do reserved instance pricing here. You're not going to shut off the routing instances, and that you're going to need at least 1 VPN instance per region. So you really want to take advantage of some of the pricing models there and really look at that RI pricing scheme. And going through some of the opportunities here, like I said, it would have been nice if we could add OSPF to this, we could add BGP to this. Those are built into Quagga, which is the old Zebra project. We could have multiple points of entry per VPC. We could use the VGW, Direct Connect. We could have a tertiary failover using, some kind, another IPsec or a VPN point-to-point. Really, it's whatever you can think of at this point. This is one example of many possibilities, but this does work. There are other ways to make it work as well. It's kind of, how creative do you want to get?
It actually sounds like I need to do a little bit of work on my enterprise solution. I'm getting some ideas as we go through this. It's good.
Excellent. So, Daryl?
Yeah, great. I'm a little disappointed, though, because it sounds like if we implement their solutions, I don't get a snow day. I can't go skiing anymore. But great presentation, guys. The solutions, if you take a look at them, they leverage so many different AWS services, from Route 53 to Amazon VPC to EC2, auto-scaling, DynamoDB. We could even use Amazon RDS, and CloudWatch. So there's so many different services that are leveraged to create this, to create these different solutions. One an enterprise solution and one an open source solution. So thank you so much for coming. Do fill out the evaluations, and thanks again.